Hello students of class 10, this is your exercise 1.4. We will start from question number 6. Demonstrate by example that the identity relation on a non-empty set is always a reflexive relation. However, a reflexive relation is not necessarily an identity relation. So in here question number 6 saying that demonstrate by example that an identity relation on a non-empty set. Okay, so first of all I will take the set. Okay, let there is a set A and its elements are 1 2 3. Okay, there is a set A and its elements are 1 2 3. So demonstrate by example that an identity relation on a non-empty set. So an identity relation on set A, okay, an identity relation, the relation is identity relation on set A, which I will take it as IA. Okay, identity relation on set A, this will be 1 1 1 2 1 1 2 2 and 3 3. Yes, this is the identity relation on set A. Okay, now this one, it is reflexive also. Yes, this is the identity relation on set A. Understand? In here, this relation, it will be reflexive relation also. You can say which is a reflexive relation. Okay. Now, if I take R is equals to 1 1 2 2, then again 3 3, then 1 2, if I take it, okay, which is this is a reflexive relation. R is a reflexive relation. Okay, R is a reflexive relation, but not identity. Okay, not identity. Understand? If I take set A, which is 1 2 3, okay, and if I take an identity relation on set A, IA, it will be this one, and this this relation, okay, it is reflexive also. Understand? It is reflexive relation also. This relation, it is reflexive relation also. But if I take another relation, R is equals to 1 1 2 2 3 3, and again one element if I add, which is 1 2, now this is reflexive. Okay, this is reflexive, but it is not identity. Okay, so in this way you can write it. Next I will go to question number 7. Question number 7, you see, let R be a relation defined on the set of natural numbers n. Okay, let R be a relation. Let R be a relation defined on the set of natural number. Defined on the set of natural numbers. Defined on the set of natural numbers n as xy belongs to R if x divides y. Okay, for all x comma y belongs to n, so that I have to show that R is not a equivalence. R is not a equivalence relation. I have to show that R is not a equivalence relation. Understand? R be a relation defined on set of natural number n as xy belongs to R if x divides y for all xy belongs to n, so that R is not a equivalence relation. Okay, so in here R, okay, R it is xy, okay, R it is xy such that x divides y. Yes, x divides y for all xy belongs to n. Okay, xy such that x divides y. Now it is a relation on the set of natural numbers n. It is a relation on the set of natural numbers, and in here x divides y. So this relation, it will be 1 2, yes, 1 2 1 3 1 4 Understand? And then again 2 4, yes, 2 6, 2 8. Okay, so in this way it will go. Understand? This is x divides y. 1 divides 2, 1 divides 3, 1 divides 4. Okay, 2 divides 4, 2 divides 6, 2 divides 8. Like that it will go on and on. 1 5, 1 6, 1 8, 1. It will go on. Understand? So in here it is saying that so that R is not equivalent. Yes, R is not an equivalence relation. Understand? In here, one thing I can add again in this set. One thing I can add. This one 1 1. Okay, 2 2. This one also I can add here 1 1. X divides y. X divides y. X divides y. Like that will go. So R is, you can say R is reflexive. Okay, R is reflexive. Understand? Okay, now you see R is not symmetric. R is not symmetric. This one you can write here. R is reflexive. Now you can write that since 1 2 belongs to R, but 2 1 does not belongs to R. Yes, x divides y, 1 divides 2, but 2 does not divides y. Understand? So 1 2 belongs to R, but 2 1 does not belongs to R. Therefore you can say R is not symmetric. Yes, R is not symmetric. Understand? R is not symmetric. Okay, so therefore directly you can say that R is not equivalent. In here R is not equivalence relation. Okay, R is not equivalence relation. Understand? R can be reflexive. Okay, R can be reflexive because in here 1 1 2 2 3 3 4 4 5 5 6 6 7 7 like that will go on and on. Understand? These elements it belongs to R. Okay, because in here 1 divides 1, 1 divides 1. Understand? 3 divides 3. Okay, 1 divides 1, 2 divides 2, 3 divides 3, x divides y. So it is obeying, the relation is obeying. So R will be reflexive, but R it will be not symmetric. Why? Because in here 1 2 belongs to R, but 2 1 does not belongs to R. Understand? Because 1 divides 2, but 2 does not divides 1. 1 divides 2, but 2 does not divides 1. Understand? So therefore x divides y. In here only saying x divides y. Okay, so therefore R is not symmetric. So since R is not symmetric, so therefore you can say that R is not equivalence relation. Okay, therefore you can say that R is not equivalence relation. Or this one also you no need to write. R is reflexive. Only you can, so that you write down the set. Understand? You write down the set, and then since 1 2 belongs to R, but 2 1 does not belongs to R, therefore R is not symmetric. Therefore R is not equivalence relation. Understand? We already know that in order for the relation to be an equivalence relation, it should be reflexive, symmetric, and transitive. Understand? Since R is not symmetric, so therefore R is not equivalence relation. Okay. Next, I will go to question number 8. Or question number, you see question number 7. One time again I am showing you question number 7. In this way also you can do. Okay, question number 7. In this way also you can do. R such that R is a relation. Okay, R is a relation on the set of natural numbers, and R, this is equals to xy such that x divides for x comma y belongs to n. Understand? So so you can say that AA belongs to R. Okay, AA belongs to R. Since A divides A, therefore R is reflexive. therefore R is reflexive. Okay, and then you can say if AB belongs to R, that is A divides B, but B does not divides A, therefore BA does not belongs to R. Okay, so therefore you can say R is not symmetric. Okay, R is not symmetric, therefore you can say that R is not a equivalence relation. R is not a equivalence relation. Like in this way also you can do. Understand? Now next I will go to question number 8 here. Okay, next I will go to question number 8. Question number 8, you see, let R be a relation defined as R is equals to xy such that x minus y is divisible by 5 for xy belongs to z, so that R is an equivalence relation, so that R is an equivalence relation. Now in your solution, okay, R is equals to xy such that x minus y is divisible by 5, okay, for xy belongs to z, so that R is an equivalence relation. Understand? So in here you can okay, in here you can say that this is, you see, A comma A belongs to R. Okay, A comma A belongs to R. Understand? Since A minus A equals to 0 is divisible by 5, okay, A minus A is equals to 0 is divisible by 5, therefore it is reflexive. Okay, therefore it is reflexive, because in here you see, if you take 1 1, okay, 1 minus 1 is what? 1 minus 1 is 0, 0 is divisible by 5. If you take 2 2, understand, 2 2, 3 3, 4 4, 5 5, 6 6, understand, all of these ordered pairs satisfy this relation, x minus y is divisible by 5. Okay, so therefore R will be reflexive. Understand? R will be reflexive. All those elements will come. 1 1, 2 2, 3 3, 4 4, 5 5, 6 6, like that, all those elements will come. Understand? It is reflexive. Next again, if I can take next again, if you see AB belongs to R, okay, if AB belongs to R, if AB belongs to R, okay, then A minus B is equals to 5m. Okay, A minus B is equals to 5m. M belongs to Z. Understand? Let's say that in here, let's say that this is A minus B is divisible by 5. Understand? Let's say A minus B is divisible by 5. So this one I am showing it in this way, that A minus B, it is equals to whatever the answer I will get, it is a multiple of 5. Understand? So this means that A minus B is divisible by 5. That I am how like writing? I am writing in this way. A minus B, okay, A minus B is equals to 5m. That means if AB belongs to R, that means A minus B is divisible by 5. Understand? If I say that A minus B belongs to R, that means A minus B is divisible by 5. This element, it belongs to the it belongs to R. Understand, this element belongs to R. Why this element belongs to R? Because a minus b is divisible by 5. That I am writing in this way. A minus b is equals to 5m, where m belongs to z. Understand? If I take minus common here, I will get this one is equals to 5m. So b minus a, this thing I can write it as 5 into minus m. Understand? 5 into minus m. So this one b minus a is equals to 5n. Understand? Where m belongs to z. Okay, n belongs to z. That means what I got? That BA belongs to R. B minus A, it is also divisible by 5. Yes, that only I got. B minus A, it is also divisible by 5. So BA belongs to R. So therefore I can say that R is symmetric. Yes, therefore I can say that R is symmetric. Understand? Since AB belongs to R, BA also belongs to R. Therefore I can say that R is symmetric. Understand? And next I will have to show that R is transitive also. Okay, next I will have to show that R it is transitive also. Okay, so therefore if AB, again I will take that let AB belongs to R. Okay, let AB belongs to R. So this one how I can write? A minus B is equals to 5m. Yes, A minus B is equals to 5m. This is our equation number 1, where m belongs to Z. And then again and let's say BC, let's again BC also belongs to R. According to transitive relation, I have to show that AB belongs to R. If AB belongs to R, BC belongs to R. Now I will have to show that AC also belongs to R. If I can show that AC belongs to R, then I can say that R is a transitive relation. So this means B minus C, it is 5n. This is equation number 2. N belongs to Z. Understand? Now equation 1 plus 2 if I do, A minus B plus B minus C is equals to 5m plus n I will get. So B cut A minus C, it is equals to 5m plus n I will get. Okay, so therefore from this you see, from this I show that A minus C, the answer that I am getting here, it is a multiple of 5. The answer that I am getting here, it is a multiple of 5. Understand? So that means what I got? That AC belongs to R. Understand? AC belongs to R. So what I said, AB belongs to R, BC belongs to R, and what I show, that AC also belongs to R. So therefore I can say that R is transitive. Therefore I can say that R is transitive. Understand? So therefore I can say that R is an equivalence relation. Therefore R is an equivalence. R is an equivalence relation. Okay, therefore I can say that R is an equivalence relation. So this is question number 9. Question number 9, it is saying that let R and S be two relations on set A. Okay, let R and S be two relations on set A. Examine whether the following statements are true. First it is, if R is reflexive. Then R inverse is reflexive. Okay, so first of all let me so in here, first of all, question number 9 solution we will do here. Question number 9 solution. So it is, let R and S be two relations on set A. Examine whether the following statements are true or false. Okay. So therefore, since R and S be two relations on set A, R and S, okay, R and S are two relations. R and S are two relations on set A. So in here, first of all, I will take let A is equals to A, B, C, D. Understand? A is equals to A, B, C, D. First of all, I will take out the A cross A set, which is our A, B, B, C, A, B, A, C, A, D, then again B, A, B, B, C, D, then again CA, CB, CC, CD, then again DA, DB, DB, then again DC, then DD. Understand? This is our A cross AC. Okay, this is our A cross AC. Now I will solve the first question. Okay, for solve the, if R is reflexive, then R inverse is also reflexive. Okay, since R is reflexive, understand, since R is reflexive, therefore R set will be AA, BB, CC, DD. Understand? And its R inverse will be what? R inverse will be, it will be same set only, AA, BB, CC and DD. So therefore I can say that R inverse is reflexive. Yes, R inverse is reflexive. So last one line I can write, therefore the following statement is true. Okay, the following statement is true. Understand? Next I will solve number B. Next I will do number B1. Okay, so in here number B it is saying that if R is an equivalence relation, then R inverse is also an equivalence relation. Okay, so since R is an equivalence relation, since R is an equivalence relation, understand? So therefore R is equals to, in this this A cross A set I will take. Understand? All of this I will take, since R is equivalence relation. So R is equals to A cross A set I will take. Understand? This is the universal set. A cross A set I will take. There all of these elements will come. Okay. So again A, B, A, C, A, D, B, A, B, 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 C, B, D, C, A, C, B, C, 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 D, D, A, D, B, D, C and D, D. Understand? So now I will take out the R inverse. R inverse will be what? A, B, A, C, A, D, A, B, 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 C, B, then again D, B, this is B, D, so this will be D, B, A, C, B, C, 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 D, C, A, D, B, D, okay, B, D, then again this is C, D and D, D. Understand? This is R inverse. Okay, so now R inverse, it will be also equivalence relation only. Understand? R inverse, it will be also equivalence relation only. R it is saying equivalence relation, that means R will be reflexive, symmetric and transitive, and R inverse, it will be also reflexive, symmetric and transitive. So therefore you can write therefore R inverse is an equivalence relation. Understand? R inverse is an equivalence relation. So therefore you can write that the following statement is true. Understand? Therefore the following statement is true. Okay, this is number B. Next I will show number C solution. Okay, next I will show number C solution. Okay, so in here number C, it is saying that if R and S are symmetric, okay, R and S are symmetric, R union S is also symmetric. So in here I can write, since R is symmetric, therefore if AB belongs to R, then BA will be also, it will be there in R. Again, since S is symmetric, so therefore if you can say that if CD, understand, if CD belongs to S, then DC, it will be in S. Understand? So therefore R union S, it will be AB, BA, CD and DC. Understand? Now R union S, this relation also what? This relation, it will be also symmetric. So therefore you can write R union S is symmetric. Understand? R union S is symmetric. So therefore the following statement is true. Okay, the following statement is true. And next the last one you see, number D. Number D, if R and S are reflexive, then R intersection S is reflexive. So in here, since R is reflexive, so therefore R is equals to, you can take, this is AA, BB, CC and DD. Understand? And again, since S is reflexive, so S is equals to, again, same AA, BB, CC and DD. Okay, so therefore R intersection S, it will be what? It will be again the same set only, AA, BB, CC and DD. Understand? It will be the same set only. Okay, so therefore R intersection S is reflexive. Okay, R intersection S is reflexive. So therefore the following statement is true. Okay, the following statement is true. Understand? This is D. Okay, this is the question number. This is D. So in this way you can do it. Now question number 10, you see, question number 10, give an example to show that the statement if R and S both are transitive is not true. Okay, R and S both are transitive is not true. So this one I will, you see, hint it is already given. Okay, hint it is already given. Let, I can say that let R is equals to 1, 3, okay, and S is equals to 3, 2. Okay, let R is equals to 1, 3 and S is equals to 3, 2. Okay, now in here I can say R is equals to 1, 3 and S is equals to 3, 2. Okay, both are transitive. Okay, both are transitive. Both of these two relations are transitive. But R union S, if I do, then I will get 1, 3, 3, 2. Okay, 1, 3, 3, 2, which is not transitive. Okay, which is not transitive. Understand? I can take two sets. This is already, it is given in your hint. Okay, from the hint only we can solve the problem. So this is, I can take that let R is equals to 1, 3 and S is equals to 3, 2. Understand? These two examples I can say. Now both of these relations, both are transitive, but R union S, if you do, you will get 1, 3, 3, 2. Now this is R union S is not transitive. Okay. Next I will go to question number 11. Okay, next I will go to question number 11, saying that let L be the set of straight lines on a rectangular Cartesian plane if we define a relation R on L as X is perpendicular to Y. Okay, the relation it is given. If we define a relation on L, R such that L to L, there is a R is a relation on N. Okay, and what is this relation? This relation is given that X is perpendicular to Y. Understand? So this is R is equals to, I can write XY such that X is perpendicular. XY such that X is perpendicular to Y. Okay, perpendicular to Y for X comma Y belongs to L. Understand? X comma Y belongs to, then state whether R is reflexive, symmetric, Okay, L it is what? It is a L it is a set of straight lines. Yes, L it is a set of straight lines. Understand? So in here it is saying that x is perpendicular to y for xy belongs to L. Then state whether or not R is reflexive, symmetric, transitive, and anti-symmetric. So this is your first one. Okay. So L it is a set. L it is a straight of L it is a set of straight lines. Okay, L it is a set of straight lines, like the straight lines are there. Understand? L it is a set of straight lines. Now x is perpendicular to y. Understand? X is perpendicular to um, x is perpendicular to y. So in here, so first of all, I have to show that in here R is reflexive. Okay, R is reflexive. Now, in here you see first in reflexive, x comma x, it does not belongs to R. Okay, since you can say, since a line cannot be perpendicular to itself. Okay, a line cannot be perpendicular to itself. Understand? A line cannot be perpendicular to itself. Okay, so therefore it is not, R is not reflexive. Yes, R is not reflexive. Next, okay, if I draw in this way L set, you will get a confusion. Let us imagine that L is a set of straight lines. Okay, there are straight lines are there. Understand? And this is R. R is a relation on L. Okay, R is a relation on L. Now it is saying that I have to show that it is symmetric. Okay, R, this relation is symmetric. Understand? Now in here you see, if I say that xy belongs to R, if I say that xy belongs to R, then yx will also belongs to R. Understand? Because you see, if one line is perpendicular to the another line, okay, one line is perpendicular to the another line, then this line is also perpendicular to the first line. Understand? If this first line is perpendicular to the second line, then the second line is also perpendicular to the yes. Let me draw it in this way. Okay, this one you see. Okay, first line is perpendicular to the second line. Understand? And second line is also perpendicular to the first line here. Okay, so therefore if xy belongs to R, if xy belongs to R, then yx will also belongs to R. Understand? I can show this in this way, that xy belongs to R, that means x is perpendicular to y. Okay, and I can say that y is perpendicular to x. X is perpendicular to y, then I can say that y is perpendicular to x. So therefore I can say that yx belongs to R. Therefore R is symmetric. Understand? R is symmetric. Okay, R is symmetric. Next I have to show that R is transitive. R it is transitive. Third one, I have to show that R is transitive. So now in here you see, if xy belongs to R, okay, if xy belongs to R, that means in here x is perpendicular to y, and yz belongs to R, okay, this means that y is perpendicular to z. Understand? So from here I can say that, you see, x is perpendicular to y, this is x, this is y, x is perpendicular to y, and y is perpendicular to z. Y is perpendicular to z. Okay, x is perpendicular to y and y is perpendicular to z. Let me take z as this one. This is our z. You see, x is perpendicular to y is perpendicular to z, but x is not perpendicular to y. Understand? X is not perpendicular to y. So therefore I can say that x is not perpendicular to z. X is not perpendicular to z. Understand? Therefore xz does not belongs to r. Therefore r is not transitive. Understand? R is not transitive. Okay, R is not transitive. Understand? And last one I have to show that R it is antisymmetry. Okay, the fourth one, R is antisymmetry. So I can take, if xy belongs to R, that means x is perpendicular to y. Okay, then y is perpendicular to x. Okay, then I can say that yx belongs to R. And x is not equals to y. Understand? X is not equals to y. Therefore, it is not antisymmetric. Understand? Therefore, it is not antisymmetric. Okay. Question number 12. Here. It is, you see, question number 12. Change the definition of R in question number 11 as x is perpendicular to y and verify the conditions. Okay, change the definition of question number 11 to x is x. Now you see R it will be xy such that x is parallel to y for xy belongs to L. Okay, x is parallel to y. So in your first one, in reflexive, okay, first one reflexive. Now x is parallel to y. So in here you see xx belongs to R, since a line is parallel to itself. In here xx will belongs to y. Understand? Since a line is parallel to itself, therefore it is reflexive. Understand? Next one, for symmetric. Now if xy belongs to L, okay, that is x is parallel to y. Okay, that is x is parallel to y. Now if x is parallel to y, then y is also parallel to x. Yes, so therefore I can say that yx belongs to R. So therefore it is symmetric. Okay, next I will check it for transitive. Now for transitive, let xy belongs to R, okay, and yz belongs to R. I will write it in this way. Let xy belongs to R. That means what? X is parallel to y. And yz belongs to R. That means what? Y is parallel to z. Understand? Y is parallel to z. Okay, so therefore what? X will be parallel to z also. Understand? If I take these three lines, this is x, this is y, this is z. X is parallel to y, y is parallel to z, and x will be parallel to z. Understand? So therefore I can say that therefore I can say that xz belongs to R. Therefore it is transitive. Understand? Therefore R is, you can say that therefore R is an equivalence. Transitive. And verify the conditions. And change the definition and verify the condition. Okay. Yes, this is the correct there. It is transitive. Understand? It is therefore R is transitive. Okay, R, it is your transitive. Okay, so R is transitive, so therefore you can say that R is an equivalence relation. Therefore you can say that R is an equivalence relation. Okay, therefore you can say that R is an equivalence relation. Understand? Next, the last one, it is question number 13 there. Question number 13 I will give you in a note. Okay, I will give you the notes. Question number 13, I will give you the notes and then I will explain it to you. Okay, so this is our exercise. Exercise 1.4, it is over. Type 1 you try to do by yourself. There is just an example you have to give of a relation which will be reflexive, neither symmetric nor transitive. R is symmetric but neither reflexive nor transitive, and R is transitive but neither reflexive nor symmetric. It is very easy there. Okay, it is very easy there. You please try to do by yourself. Understand? So with this, our set chapter, it is over, and our complex number chapter, this is also over. So both of these chapters are over. Next I will go to arithmetic of integer. If any topic I have to explain it again, you please write it in the comment section. I hope you have understood. Thank you.